Hi everyone. In this video I am starting lecture series of Applied Mathematics 4 of second year engineering IT branch. Let us start with the topic number theory. Number theory is a branch of mathematics that deals with the properties of integers, and it has found that it has ever interesting applications in crypto system and computer science. So in this video, we will see what is divisibility and Euclids algorithm. What is divisibility? Let us see its formal definition. An integer b is said to be divisible by non-zero integer a if there exists some integer k such that b is equals to k into a. That is, when we divide this integer b by a, if we are getting quotient as whole integer, then we say that this number b is divisible by a. That is, if we are getting remainder as 0, then we can write this integer b as product of quotient and divisor. If we cannot find such an integer, that means if we are not getting quotient as integer, if we are getting it as a fraction, then we say that b is not divisible by a. For example, 35 upon 5 is 7. Here we can see that quotient is integer. So we can write here 35 as 7 into 5. So we can say that 5 divides 35. Now in case of this, 18 upon 4 is 4.5. Here quotient is not integer. Right? That is, remainder is not 0. That's why we are getting quotient as fractional number. So in this case, there does not exist any integer in z such that we can write 18 as product of quotient and divisor, where quotient is some integer. So in this case, 4 does not divide 18. Now here again, if you can write 78 can be written as minus 9 into minus 8. So we can say that 72 is multiple of minus 8. So we can say that 72 is divisible by minus 8, or minus 8 is divisor of 72. So whenever we say that a divides b, then we denote it by this notation. And when we say that a does not divide b, then we will denote it by this notation. Now let us see what are the properties of divisibility. For some integers a, b, c, following holds. Note that in all following cases, whenever we will consider these integers a, b, c as a divisor, they are non-zero, because divisor must be non-zero. So first property is a divides 0, 1 divides a divides a. This is pretty obvious property because we know that 0 is divisible by any integer, 1 divides any integer, and any integer divides itself. So this is obvious. Next, a divides 1 if and only if a is equals to plus or minus 1. Now in this case, a divides 1. So by definition of divisibility, 1 is equals to k times a, where k is quotient, that is any integer. So to hold this equation, 1 is equals to k into a, the value of a cannot be other than plus or minus 1. So this you can verify. Next, a divides b and c divides d, then product AC divides product BD. So for this, let us take one example. 2 divides 4, 3 divides 9, therefore product 2 into 3, that is 6, and 4 into 9, that is 36. So we can verify 36 is divisible by 6. Here quotient is 6, right? So next property, if a divides b and b divides c, then a divides c. So in this case, we can take one example again. 7 divides 56 because 8 is a quotient which is integer. 56 divides 168 because 3 is a quotient which is integer. So if we can replace this 56 by 8 into 7, and we can write it as 168 as 24 into 7. So here this 24 is nothing but quotient which is integer. So 7 divides 168. So this property is again verified. A divides b and b divides a if and only if a is equals to plus or minus b. So this property says that if some integers are divisors of each other then the relation between them is they are associates of each other. That is, A is equals to plus or minus 1 times B. That is, they are associates of each other. So this you can verify. If A divides B and B is non-zero, then absolute value of A is less than or equals to absolute value of B. So we know that the value of divisor cannot be greater than value of dividend. So again you can verify this property. If A divides B and A divides C, then A divides Bx plus Cy, where x and y are some arbitrary integers. That is, A divides linear combination of B and C. So for this, let us take one example. We know that 5 divides 25 and 5 divides 50. So if we will take x as 4 and y as 7, and if we will calculate this term, we will get it as 450, and we can verify 450 is divisible by 5. So these are the all properties of divisibility. Now let us see what is division algorithm. Its statement: for given integers a and b with b strictly greater than 0, there exist unique integers q and r satisfying a is equals to qb plus r with 0 less than or equals r strictly less than b. The integers q and r are called quotient and remainder in the division of a by b. Now this theorem says that if you will divide this integer a by b, then there exists unique quotient and unique remainder which satisfies this equation. That is, a is equals to quotient into divisor plus remainder, with the restriction on remainder is that the value of remainder can be 0 or greater than 0 but strictly less than divisor. So this is the theorem. The corollary based on this theorem is, which is same, just the difference is in theorem we have assumed the value of b as positive integer, that is strictly greater than 0. In this corollary we are assuming the value of b as just non-zero, that is b can be negative as well. So in that case, the equation which is satisfied by a and b and q and r is a is equals to qb plus r with the value of remainder is strictly less than modulus value of b. So divisor, if it is negative, then its absolute value, whatever it is, the value of remainder is strictly less than that. So we can verify by taking one example. Here we can take a as minus 59 and b as minus 7. Then if we will apply this division algorithm, we can see here the value of remainder is strictly less than the value of absolute value of divisor, that is mod minus 7, which is 7. So this is division algorithm. By using division algorithm, let us solve one example. We want to prove that product of 3 consecutive integers is divisible by 3. So for this, consider 3 consecutive integers a plus 1, a plus 2. So let us divide this integer a by 3. Then by division algorithm we will get a is equals to 3k plus r with 0 less than or equals r strictly less than 3. So if we divide this integer a by 3, then we will get some quotient k and some remainder r such that a is equals to 3k plus r, with the restriction on this remainder r as r can be 0 or greater than 0 and strictly less than divisor, that is 3. So by using this restriction on r, we will get a in 3 possible forms. These forms are as follows. If r is equals to 0, then a will be 3k. If r is 1, then we will get a as 3k plus 1. If r is 2, then we will get a as 3k plus 2. So these are the 3 possible forms for a. So in each of these possible form, we will prove that these integers, from these integers a plus 1, a plus 2, one of the integers will be like this, which will be divisible by 3. So let us prove it. So in first case, if a is in the form of 3k, that is this first integer, which is itself by definition of divisibility divisible by 3. So for this first integer, it is pretty obvious. Now for second case, if we will consider this third integer a plus 2, and if we will take this form, so we will get a plus 2 as 3k plus 1 plus 2, which can be written as 3 times k plus 1. So in second possible case, this third integer a plus 2 is divisible by 3 because we are getting it as a multiple of 3. So in second case, 3 divides a plus 2. Now in third case, if a is in the form of 3k plus 2, then if we will take this second integer a plus 1, then we will get it as 3k plus 2 plus 1, which can be written as 3 times k plus 1 again. So in this case also, a plus 1 is divisible by 3. So in all these possible forms, we are getting either a or a plus 1 or a plus 2 as a divisible by 3. So if we will take this product of a plus 1, a plus 2, then if one of the integer is divisible by 3, then whole product is integer is divisible by 3. Hence the proof. Now before proceeding towards Euclid's algorithm, let us define GCD or greatest common divisor. Let a and b be given integers from which one of them is non-zero. Then greatest common divisor or GCD of a and b is a positive integer d which satisfies following conditions. First one, d divides a and d divides b. And second condition, if c divides a and c divides b, then c is less than or equals to d. So what this definition says, if we are saying d is a GCD of a and b, then first condition says that d must be divisor of both a and b. And second condition, if c is any other divisor of a and b, then c should be less than or equals to d. That is, d is the greatest among all common divisors. So to denote this GCD, we always use this notation. For example, let us find out what is GCD of minus 12 and 30. So to do this, let us collect all possible positive divisors of minus 12. So which are as follows: 1, 2, 3, 4, 6 and 12. And all positive divisors of 30 are 1, 2, 3, 5, 6, 10, 15 and 30. So among all these positive divisors of minus 12 and 30, common divisors are 1, 2, 3 and 6. So among these all common positive divisors, 6 is the biggest positive common divisor. Therefore, GCD of minus 12 and 30 is 6. There are obvious results which can be derived from definition of GCD itself. First one, GCD of a and 1 is 1. We know that possible divisors of 1 are plus or minus 1. So, greatest positive common divisors of 1 and a cannot be other than 1. Second one, GCD of a and 0 is mod a. We know that GCD is a positive term, and we also know that 0 is divisible by any integer. So, greatest common positive divisor of a and 0 is mod a. Now, GCD of AB or GCD of B and A or GCD of minus A and B or GCD of A and minus B or GCD of minus A and minus B is same as GCD of mod A and mod B. Why? Because GCD is nothing but a positive term. So, whatever value we will get here, it will be same as for all of these. So, you can verify these results by taking examples. The greatest common divisor of two integers can be found by listing all their positive divisors and choosing the largest among common divisors. But this is difficult and lengthy way for large numbers. A more efficient process is using repeated application of division algorithm. How? This process of applying division algorithm repeatedly is called Euclidean algorithm. Let's see what it is. Let us see what is Euclid's algorithm. Let a and b be the two integers whose GCD we want to calculate. As we have seen, GCD of a and b is same as GCD of mod a and mod b. Therefore, there is no harm in assuming that both a and b as a positive integers. So one more added condition here, we will assume a is greater than or equals to b. Now we will apply division algorithm to these integers a and b to find unique integers q1 and r1, which are nothing but quotient and remainder, which holds this condition. Now in this step, if we are getting this remainder r1 as 0, then we will stop here and we will say GCD of a comma b is b. Because if remainder r1 is 0, then here we can see that by definition of divisibility, b divides a. So greatest common positive divisor of a and b is nothing but b. If we are not getting r1 as 0, that is if r1 is not 0, then we will proceed further by taking b as a dividend and r1 as a divisor. So we will again apply division algorithm to b and r1 to produce integers q2 and r2, that is quotient and remainder, which holds this condition. So in this step, if we are getting this r2 as a 0, then we will stop here. If we are not getting r2 as a 0, then we will proceed further by assuming r1 as dividend and r2 as divisor. So again we will get some q3 and r3 which holds this condition. So in this way we will repeat this procedure further. We proceed in this way. So this process of applying division algorithm goes on until some 0 remainder appears. So let us say at n plus 1th stage we get remainder rn plus 1 equals 0. Here we can see that we have taken rn plus 1th remainder as 0. So this implies this rn divides rn minus 1. Here we can see, right? So note that we will get 0 remainder sooner or later because the decreasing sequence of non-zero remainders cannot contain more than b integers. Always remember. So this entire procedure gives us following set of system of equations. So thus Euclid's algorithm says that this last non-zero remainder in this entire procedure is GCD of a and b. Here we will argue that this Rn is GCD of a and b. So this is Euclid's algorithm. Let us solve this example. We want to find out GCD of 12,378 and 3054 by using Euclid's algorithm. Okay. So here we will consider this bigger number as dividend and this smaller number as divisor. So let us apply division algorithm to these two numbers to get quotient and remainder. So after division we got quotient 4 and remainder 162. You can verify it. So here we can observe that this 162 is not 0. So we cannot stop here. So we have to repeat the procedure of division algorithm in next step. So in next step we will consider this divisor, that is 3054 as a dividend and this remainder 162 as a divisor to get next quotient and remainder. So in next step we get this. So in this step we get quotient 18 and remainder 138. So again we are not getting here remainder 0. So again we have to apply division algorithm. So in next step we take this 162 as dividend and 138 as divisor. So in next step we got quotient 1, remainder 24. So again remainder non-zero. So again apply the same division algorithm. So here we got again non-zero remainder. So again apply division algorithm. So here we got remainder 6 which is non-zero. So we'll again apply. Okay, in this step we got remainder 0. We can see here, right? So by Euclid's algorithm, it says that the last non-zero remainder is nothing but GCD. So here in this procedure, last non-zero remainder is 6. Therefore, GCD of 12,378 and 3054 is 6. So you can calculate GCD in this way. Let us see this important theorem. For given integers a and b, not both of which are 0, there exist integers x and y such that GCD of a and b is equals ax plus by. So this theorem says that for any integers a and b, we can write its GCD as ax plus by, where x and b are some integers. So for this, let us solve an example so that we will understand. So in previous example, we have calculated GCD of 12,378 and 3054, which was 6, right? So whatever procedure of applying division algorithm and getting that equations we did, so that is this, right? So we'll use it to express GCD in this form. Okay, so what we will do is we will start with second last step in these equations and we will eliminate these remainders that are 18, 24, 138, 162 respectively. Okay, so let us start with second last equation from this. Okay, so from this we can write 6 as 24 minus 18, because here we can shift this 1 into 18 to LHS and we can write this, right? Now secondly, we will eliminate this 18 by using this equation. So here we can see that 18 can be written as 138 minus 5 into 24, that is this, right? So after solving this, after expanding this bracket and collecting coefficients of 24, we will get 6 into 24 minus 138, right? Because 1 plus 5 minus plus, so 1 plus 5 will be 6, so we'll get this. Now we will eliminate this 24 by using this equation. So here we can see that 24 can be written as 168 minus 138 by shifting this to LHS, right? So we'll get it as like this. Now we will collect coefficients of 138. So here we can see that minus 6 minus 1, that is minus 7. So we got this term. Follow? Now next we will eliminate this term 138 by using this equation, right? So 138 can be written as 3054 minus 18 into 168 by shifting this term to LHS. So we will get this equation, right? So now we will collect coefficients of 162. So 6 plus 7 into 18. So we will get it as 132. So what is? So 132 into 162 minus 7 times 3054. So we got it, right? Now in next step we will eliminate this 162 by using this equation, which is last, right? So 162 can be written as 12,378 minus 4 into 3054. So in this way. Now we'll collect coefficients of 3054 and it will be minus 4 into 132 plus minus 7. So that term will be minus 535 and coefficient of 12,378 is just 132. So here we can see that we have expressed this GCD 6 in the form ax plus by, where x is 132 and y is minus 535. These are some problems for practice. You can solve all the problems in the same manner as we did. Let us define least common multiple, that is LCM. The least common multiple of two non-zero integers a and b is a positive integer m which satisfies following conditions. First condition, a divides m and b divides m. That is, both integers divides their LCM. Second property, if a divides c and b divides c, where c is some positive integer, then this LCM is always less than or equals to c. So this is the definition of LCM. For example, the positive common multiples of integer minus 12 and 30 are 60, 120, 180 and so on. We can get infinite common positive multiples, right? So among all of these, 60 is least one, right? Therefore, LCM of minus 2 and 30 is 60. Now note that for any two non-zero integers a and b, LCM always satisfies this condition. That is, LCM of a and b is always less than or equals to modulus of their product. Always remember. Now there is a theorem which defines relation between GCD and LCM. That is this: for any positive integers a and b, product of GCD and LCM is same as product of integers. Always remember. That is, GCD into LCM is equals to their product a into b. And corollary based on this, if we have GCD of a and b as 1, then obviously by using above theorem, LCM will be just product. Clearly, if GCD is 1, then LCM will be just product AB, which is obvious. Above theorem makes the calculation of the least common multiple of two integers dependent on the value of their greatest common divisor, which can be calculated from Euclidean algorithm. We have seen it, right? So we have calculated GCD of 12,378 and 3054, which was 6. So by using above formula, we can find LCM of these two numbers, which is just their product divided by GCD. So which is nothing but this digit. These are all immediate consequences of theorems which we have studied. You can read it for your extra knowledge. So that's it for this video. Thank you. In next video we will see modular arithmetic. So stay tuned.